Did you know the math we're about to discuss is the reason your phone can store more photos and your calls stay clear? Hi, my name is Janssen Hugo, together with my groupmate Dela Cruz to tackle orthogonal and orthonormal vectors.
Now, let me discuss orthogonality, orthogonal and orthonormal vectors. First is the orthogonal vectors. Orthogonal vectors is a two vectors A and B are perpendicular to each other. That is, if the angle between the two vectors is 90 degrees, then the two vectors A and B are said to be orthogonal vectors. We know that the dot product is represented as the product of the magnitudes of the two vectors along with the cosine of the angle between them. The angle between the two orthogonal vectors is 90 degrees, so cos theta equals cos pi by 2, which is equal to 0. And hence, the dot product is equal to 0, so the dot product of the two orthogonal vectors is equal to 0. Let us now discuss an example. Find the vectors u1 and u2 are orthogonal vectors or not. To find the dot product of the two vectors u1 and u2, let us multiply the corresponding elements of the vectors and add the products. We get the dot products as 0, so we can say that the two vectors are orthogonal vectors. Let me provide another example. Find the vectors u1, u2, and u3 are orthogonal vectors or not. Now find the dot products of the two vectors u1 and u2 by multiplying the corresponding elements of the two vectors and by adding the products. We get the dot products of u1 and u2 as 0. Now find the dot products of the two vectors u2 and u3 in a similar way. We get the dot products of u2 and u3 as 0, and also the dot products of u3 and u1 is 0. By observing all the three dot products, we can say that all the three given vectors are orthogonal to each other. Now, let's proceed to orthonormal vectors. Orthonormal vectors, if two unit vectors A and B are perpendicular to each other, then they are called orthonormal vectors. The magnitude of each vector is equal to 1 and the dot product of the two unit vectors is 0. For example, I and j are unit vectors along x and y axis, so these are orthonormal vectors. In the same way, j and k and I are orthonormal pairs of vectors. Here, we need to note that if A and B are two vectors such as their dot product is 0, then the unit vectors A by mod A and B by mod B of the two vectors become orthonormal vectors. Let us now discuss some examples. Find the vectors A, B, and C are orthonormal vectors or not. As the given vectors are along the x, y, and z axis respectively. The respective angle between any two vectors is 90 degrees, so we can say that the given vectors are orthogonal to each other, and also we can see that the length along the axis is 1 for all the three vectors, so we can say that the given vectors are orthonormal vectors. Here's another example. Find the given vectors are orthonormal vectors or not. Let us assume that given vectors is A, B, and C. Now find the dot products AB, BC, and CA. The dot products of two vectors A and B can be found by multiplying the corresponding elements and adding the products. Here, we can get the dot products of A and B as 0. Similarly, the dot products of the two vectors B and C can be found here. We get the dot product of B and C as 0. In the same way, we get the dot product of the two vectors C and A as 0. By observing the three values, we can say that all the three vectors A, B, and C are orthogonal to each other. Now, let us find the length of the three vectors the length of the vector A is found using the square root of the sum of the squares of all the elements. Here we get the length of vectors A is 1. Similarly, the length of the vector B is 1, and the length of the vector C is 1. So the given vectors are also unit vectors, hence we can say that the given vectors are orthonormal vectors. Here's an important note. Is a real matrix A is orthogonal if the inverse of A equals to transpose of A. In conclusion, orthonormal vectors build on this by combining orthogonality with unit magnitudes, ensuring not only perpendicularity but also normalized length.
Now that we understand what our orthogonal and orthonormal vectors are, let's look at how we can actually create them from any set of linearly independent vectors. This is where the Schmidt process comes in. So, what is the Schmidt process? The Gram-Schmidt process is a method in linear algebra that takes a set of vectors and transforms them into an orthonormal set. In other words, it straightens out the vectors so they are perpendicular and makes them a unit length, while still spanning the same space as the original set. The main idea is, imagine that you have a slanted coordinate axis. The Gram-Schmidt process adjusts them so they are perfectly at the right angles. This makes the calculation much easier because of the orthogonal vectors don't overlap in the information that they carry. So, for the example, use a Gram-Schmidt process to orthogonize these vectors. For our vector 1 is 1, 1. For our vector 2 is 1 and 0. For, for the first vector is simple. U1 is equals to V1 is equals to U1. Since wala naman na may minus sa V1 sa unahan niya. If meron, dun tayo magma-minus. Like this for V2, kasi nasa unahan niya yung V1, need natin i-minus yung V1 for V2. So this will be our chart of V's for the given starting set. This is the V's. U's will be used for the orthogonalized set, and E for the orthonormal set. So, for the second vector, we're going to remove the part of V2 that lies in the direction of the U1 para hindi sila mag-intersect. This is done using the projection. So, this will be the equation for the projection. So, V2 times U1. Since first V2, 1 times another V1 times 1 again. So it's 1, 1. Then for this is another V2, then this is V1. Just repeat it under, then equivalent will be 1 half times 1, 1. Then equivalent to 1 half and 1 half. So next, to get the orthogonal, subtract the projection to get the U2. Sorry, this is supposed to be U2. So, to get U2, you need V2 minus the projection of V2. So, it will be 1 and 0 minus 1 half and 1 half. Equivalent to 1 half and negative 1
Then
half.
minus 1
So,
half
to check
to 1 half.
for orthogonality, for a quick check, it will be V1 times V2. So 1, 1 times 1 half and negative 1 half. equivalent to be 0. So this is orthogonalized. So this will be our orthogonalized set. U1
We
is
are
equals
going
to
to get
1, 1,
the
and
norm
U2 is
of
equivalent to 1 half and negative 1 half. Now, for going for orthonormalized, U1. This is the sign for norm. So, the equation for norm is both of the 1, 1 from the existing 1, 1 orthogonalized set will be in this two part. So, the norm is equals to square root of 1 raised to 2 plus 1 raised to 2, equivalent of square root of 2. Now, E equals. Now, kukunin natin yung orthonormal set, which is E1. To get this, you need U1, which is the orthogonalized set, divided by the norm of U1. So, equals to, when you divide this 2, equivalent will be 1 over square root of 2. And 1 square root of 2. Then 2 of this. Now, this is the orthonormal set. For the next part, for the U2, first, we'll get the norm of U2. To get this, you need the square root of 1 half raised to 2 plus negative 1 half raised to 2 be equivalent to 1 over the square root of 2. Now, for the orthonormal set, we're going to divide the orthogonalized set to the norm of U2. So, equivalent will be 1 over square root of 2. And negative 1 square root of 2. So, overall, our orthogonalized set is 1, 1 and 1 half and negative 1 half. For our orthonormal set, our values are E1 is equals to 1 over square root of 2 and another 1 over the square root of 2. For U2 naman, our U2 is equivalent to 1 over the square root of 2 and negative 1 over the square root of 2. Now, let's proceed to the application in data compression. Why is this useful? In data compression, like JPEG images or MP3 audios, signals are expressed in terms of orthogonal basis functions. The Gram-Schmidt can generate those orthogonal bases. By using them, we only need to keep the most important coefficient, which is reduces the file size without losing much quality. This means by using the Gram-Schmidt, we can reduce the file size without losing much quality. Now, for the application of signal processing, in signal processing, orthogonalization helps separate signals that overlap to reduce noise and allow multiple signals to be transmitted without them interfering. For example, in wireless communication, orthogonal signals let different channels coexist without mixing them up. Just like when you're going with a call. Since madaming signals yan, if wala yung orthogonalization, mag-overlap yung call nyo with another person. So, hindi kayo magkakaintindihan. Then, iba-iba yung maririnig mo. With the help of this, na-isolate niya yung mga signals without them mixing up. In summary, the Gram-Schmidt process is a systematic way to produce orthonormal vectors. It removes redundancy, makes computation simpler, and is applied into many areas like data compression and signal processing. In short, it takes something messy and organizes it into a clean and efficient form.
In the end, inner product spaces orthogonality and the Gram-Schmidt process
aren't just abstract math, they are powerful tools shaping the technology we use every day. Thank you for listening. My name again is Janssen J. Hugo and my groupmate Dela Cruz. Thank you for everything. Goodbye, everyone.